Okay, well, since I've been given the mandate of talking about Mars and the atmosphere of climate of Mars, I want to begin with a statement of the problem of the atmosphere of Mars, at least as I see it from the point of view of impact erosion of its atmosphere. If we could have the first slide, please. This is an image of Ravi Vallis on Mars. It's a picture probably most of you have seen many times before. Let's see. Okay, there we go. This is a area of chaotic terrain. It's about 20 kilometers across. It's not a really major feature on the planet. But the interesting thing is to see these obviously streamlined valley exiting from this area of chaotic terrain. This is known technically among the cognoscenti as an outflow channel. And after much argument and lots of heat spent on the problem of the origin of these outflow channels, it's generally felt that it requires liquid water to form the outflow channel, but the water that formed it need not be stable on the surface. And that comment may lead me to remind you that at the present time, with the Martian atmospheric pressure of only about 6 millibars, water is not stable in most areas of the Martian surface. That pressure is below the triple point of water, and so if you had liquid water on the surface, some of it would freeze, some of it would evaporate, but it would not remain liquid very long. And that has been a long-standing problem of reconciling that fact of water's instability with the evidence of fluvial flow that's seen in this channel. However, if these are really the result of catastrophic floods of water released from this area of chaotic terrain, the water didn't have to be stable long. It takes a finite amount of time, even at 6 millibars, for the water to alternately evaporate and freeze, or partly evaporate and partly freeze. And in that time, especially with the jostling and so on developed in the outflow, it may have been not required that water was stable on the surface to create valleys like this. However, the next one, can I run this, by the way? Yeah, okay, good. The next one is Nergal Vallis, 800 kilometers long. Again, something probably most of you are familiar with. This formed under conditions that don't seem to require rainfall. Valleys like this with the very short meander wavelength, the fact that it doesn't branch very much, the lack of tributaries, is very similar to many canyons seen in places particularly along the Columbia River and also on the Colorado Plateau, that suggests that this valley formed as a result of sapping. That is, groundwater in the rocks flowed into the channel, and the channel evolved by cutting headward in this terrain, totally fed by groundwater. In this case, though, we require water to be stable on the surface because it implies a long-term flow, even though there's no implication of rainfall for this particular valley. Evidently, the atmospheric pressure at the time Nergal Vallis formed was large enough that water would be stable on the surface. Finally, we have a network called a dendritic network here, but the largest crater is about 20 kilometers across here. Well, that'd be this one. In this case, the dendritic pattern of the channel, the main channel with many, many feeders, the fact that it branches in this entire area suggests to most of the people who've investigated it that this kind of channel network had to form as a result of rainfall on the surface. So as we go back in time, we see more and more evidence on Mars for the existence of water in the atmosphere, even though it's not stable at the present time. This is summarized by a slide I borrowed from my colleague Vic Baker at University of Arizona. This is basically time measured in units of crater density. 0 is the present time, and as we go back, the crater density increases, and we go from Amazonian to Hesperian to Noachian, these terms for Martian geologic eras. And you can see that in general, we have there are some late networks. These are details of Baker's that I don't really want to get into. Most of the valley network formation, though, was back here in times of the most ancient plains of Mars. As we come up to more modern times, there's less and less evidence for rainfall, although there are a couple of late networks that have been observed on some of the volcanoes that are a little bit of a mystery. In general, though, it appears that the further back in Martian history you go, toward the era of late bombardment when crater densities were high, the more evidence there is that there's been some kind of water flowing and stable on the surface. So evidently the geology here records a steady decrease of the atmospheric pressure of Mars over time. I should say that the atmospheric pressure required to stabilize water on the surface is only a few tens of millibars, 12 millibars or something, is enough to allow water to be theoretically stable. However, in order to get the temperature of Mars up to the point where evaporation, condensation, and so on would be common, it's estimated by Owen and other people that something like a bar of CO2 is required in order to get enough greenhouse warming to make water a common occurrence on the surface. So the question is, then how is it that Mars lost its early atmosphere? In the series you have heard and will hear other speakers talk about silicate carbonate atmospheric interactions, other possibilities. In fact, if I could have the first view graph, that will be a summary of the different methods of escape that have been suggested. Genes escape, hydrodynamic escape, which may have been important early in the history of Mars, chemical weathering. What I want to focus on today is impact erosion, since that's the process that I'm most familiar with. Now, in talking about this process of impact erosion, I don't want to give you the impression that that's the only thing that I think is important in controlling or regulating the atmospheric pressure of Mars. It's merely the one that I'm most familiar with, and I want to try to outline it as a process. These other processes undoubtedly went on at the same time in conjunction with impact erosion, and in order to fully understand the evolution of the atmosphere of Mars, we have to put all these together, along with, besides the depleting mechanisms, we also have to add potential outgassing as a mechanism for putting gases back into the atmosphere. So the real elucidation of the history of the atmospheric pressure of Mars is a complex one involving many processes, and I don't want you to lose sight of that today in the process of focusing on just this one process. But impact erosion, in fact, is not very well understood, and that's what I've been working on lately to try to clarify what's going on. Okay, if we could have the view graph off and the next slide. Okay, I'm going to be go at this in a gradual way, talking about the different processes that can remove atmospheric gases, and I'm going to be fairly tutorial about it, so I'm going to go slowly and work up to what I think is the main process. But there are a couple of red herrings in the way, that not all things that I worked on myself, but the first real discussion of ejection of the atmosphere was by Walker, who looked at what happens when a projectile enters the atmosphere of a planet and directly ejects it. That is, the projectile enters the atmosphere, produces a shock wave. That shock wave heats the gases, gives them velocities, and Walker originally made some estimates of just how much atmospheric gas could be ejected in this way from the Earth as well as from other planets. His conclusion was, I won't go into a great deal of detail about how he did this. His conclusion, though, was that at most you could eject an amount of material comparable to the amount of atmosphere traversed by the projectile. If you imagine the projectile as a sphere and it travels some trajectory from space to the surface, it sweeps out a cylinder. If you add up all the atmosphere in that cylinder, the total mass, he estimates that about 2 or 3 times that total mass intersected by the projectile could be even theoretically ejected from the planet. In the case of Earth, he believes there's an upper limit that nothing would be ejected from the Earth, but in a planet like Mars with smaller gravity, you could get a total loss of a couple of times the atmospheric mass traversed, which, although for some purposes is significant, even if you add up all the impacts that have taken place over Martian history, doesn't account for a large percentage of, say, a 1 bar atmosphere. And so I'm not going to consider the process in any greater detail from here on. Now, the next possibility that occurred to people, and this is something that Tom Ahrens worked on for a bit, is that when the impact occurs, it throws out a lot of solid ejecta. Now, this ejecta might just be fast enough to drive some of the atmospheric gases before it and cause it to leave the atmosphere, or leave the escape velocity, exceed the escape velocity of the planet, and leave the planet that way. If we could have the next view graph. Most of you are familiar with the idea that when an impact occurs, it throws out a plume of fast ejecta. This is a result of an impact experiment done by Peter Schultz and Don Galt. You see different time frames, the development of the classic ejecta plume. The problem with this, as far as ejecting atmospheric gases go, is that although this plume is spectacular and fast-moving in a laboratory frame, and something geologists have studied in great detail, in fact, for purposes of ejection from a planet, it's very slow. The maximum ejection velocity of this kind of flow is about 1/10 of the impact velocity. So for Mars, you'd have to have impactors 50 kilometers per second or faster in order to have any part of the classic ejecta curtain exceeding its escape velocity. So this, although is maybe the first thing that comes to mind, in fact is not a particularly good source of fast ejecta that might throw off atmosphere. If I could have the next view graph. However, there is a component of very fast ejecta, one that I've talked about in some detail for other reasons, as a means of delivering SNCC meteorites from Mars to the Earth, for example. This involves treating, well, never mind the mathematics. When an impact occurs, it produces a shock wave at this equivalent center as I've represented it here. Although the shock wave travels as a compressional wave away from the impact site, in fact, when it reflects off the free surface, it produces a tensile wave. In the process of producing that tensile wave, both the ejecta, the material that's thrown off, receives a very low shock pressure compared to more deeply buried material. It also receives a very large particle velocity outwards. Ejecta thrown out in this way may achieve a velocity of 1/2 the speed of the impacting projectile and therefore easily exceed escape velocity of a planet like Mars or the Earth. In case people here believe that this is totally a theory, which I guess this simplified diagram may suggest, we'll have the next view graph, which is courtesy of Robert Schmidt at Boeing, who did some experiments of firing a small aluminum projectile into, this is water, and this dark black line is a meniscus, at in this case 3.5 kilometers a second. These are different sequences of a very high framing rate camera. What you may be able to see is this, along the side of this plume, which is water vapor, you can also see some smaller dark material. That's liquid water. That's the spalled material that I was talking about. And if you make measurements off the photograph, you discover it's moving at just about half the impact velocity. This is not unique. There have been other, maybe not so clear demonstrations of the very high ejection velocity of material from the free surface of the target in other experiments on solid targets in particular. So there's very little question now, I think, that you can get very high velocity material ejected just from the free surface. Next
stuff looks even faster.
The black stuff is faster, yes, that's vapor. And we'll talk about that in the middle, in a moment. We're working up to that. Next view graph. The idea here is that we have a projectile strikes the target, and some of the surface right near the target is ejected at high speed. The atmospheric gas, this is drawn for the Earth, so I said air, but think of it as atmospheric gas on Mars, say, is driven by the expanding ejecta and could, in this case, achieve escape velocity. Well, we can...
The difference between this process and the previous one seemed like the same thing.
Oh,
In both cases.
yeah, that's right. But in the previous one, it's during the traverse of the atmosphere. I'm supposed to repeat questions. The question was, what's the difference between this process and the previous one? In the previous one, the atmosphere was directly ejected during traverse by the projectile. It didn't even have...
Ejecta. Ejecta drove it off. Aaron's process, ejecta.
That's what I'm talking about here. The first process was direct ejection by the shock wave during atmospheric passage.
That's the one I mean, but
Well, then you had several types of ejecting.
yeah, you had another ejecta process which you
This is the
rejected,
third
and now
one.
you got another ejecta process
Okay.
which you're accepting. I don't see the difference.
The classic ejecta curtain, which I showed an example earlier, moves at too low a velocity. Most of that material moves at a velocity less than 1/10 the impact velocity.
Yeah, you said
It
that,
comes
but
out very
what's
late.
the difference with this process? It seems like eject all the same. I don't see what's different, but why does
This
something
this
fast-
this ejects. This sends out solid material much faster
Why?
than the
What's
other
going on
process.
that's different?
Because this is a result of stress wave interactions near the free surface. In the other case, where we have velocities established in the target as a result of stress wave compression and then release. It's a process that depends upon thermodynamic irreversibility, doesn't impart that much velocity to the target. Whereas near the free surface, because of the stress wave reflection, you get ejection at velocities close to the particle velocity in the shock wave. In the case of compression of the target rocks, they were originally compressed up to high speed, which is close, well, the speed of the particle velocity in the target, and then when a rarefaction comes along, that velocity is decreased. I've got a slide a little bit later that I think will demonstrate that somewhat better than this. Okay, if I could have that off, and we'll go to the next slide. This is a result of some calculations with using the speed of the spalled material and the volume of the spalled material for different impact velocities. This is for the Martian atmosphere. What we find is that this is the air ejected by this fast component of ejecta divided by the air traversed. And we see that even up to 70 kilometers a second, which is in fact faster than anything bound to the solar system can impact Mars, you get at most 5 times or so the amount of atmosphere traversed. It's not that much more effective than the direct atmospheric ejection that Walker studied earlier. And normalizing it another way, this is the same calculation, but normalized in a slightly different way. This is the air ejected divided by the air above the tangent plane. The tangent plane is a plane that just touches the surface of Mars at the impact point. And if you look at all the atmospheric mass above that, you get this mass above the tangent plane. You see that for different size projectiles, they can eject more and more mass, but even at very high impact velocities, they can eject at most, a 100-kilometer projectile can at most eject 1% of the mass above the tangent plane. This is, as we'll see compared to the vapor plume in a moment, this is not very efficient. And so I have to conclude from this that the solid ejecta are not very effective at ejecting atmospheric gases either. Now the last mechanism is ejection by the vapor plume, and in the experiments you saw, that was obviously the most high-speed and densest part of the ejecta. The idea in this case is that a projectile comes in, strikes the target, vaporizes, and it's that vapor that expands out, expands faster than the high-speed ejecta, virtually faster than anything else coming out of the crater, and in the process of expanding away, runs into the atmospheric gases and can carry the gases away with it. And what we found, as I will describe in more detail, is that this mechanism is actually quite effective at removing atmospheric gases, certainly compared to the other two mechanisms. Before I go into more detail on it, I want to look in a little bit further at the impact process itself and just how it is that impact vaporization can occur, what the vapor plume is like. And I think this will answer some of your questions, Barclay. This is a schematic of a meteorite impact. The meteorite travels in here, impacts the surface. This is illustrating things a time of a couple times the length of time that the shock wave requires to traverse the projectile. The impact produces a shock wave which has an almost hemispherical form and expands away from the impact site. Once the projectile strikes the impact site, because its back is open to free space, a rarefaction wave propagates in and quickly unloads the projectile from the very highest pressures down to a low pressure. These rarefaction waves propagate in following the main shock wave and end up giving the pressure profile the shape of a hollow hemisphere. The pressures are highest on the hemisphere, pressures are low behind the expanding shock wave, and of course low in front, because nothing in front of the shock wave has yet been affected by the impact. This line, A prime, is to give you an idea of a section of the shock wave. And here, if we look at pressure as a function of distance away from the impact, we see the pressure goes to a maximum on the hemisphere and then drops off. As it expands, going from the solid to the dotted portion, the pressure also declines as 1 over distance either squared or some higher power in the nonlinear regime. And so the shock wave expands out, and as it expands and engulfs more material, it also gets weaker. I hadn't planned to talk about it, but since Barclay asked the question, let me also mention what the particle velocity does. On the shock wave, it reaches some peak of particle velocity and then declines, usually by about a factor of about 5. But it doesn't actually go to 0. It in fact stops at some residual velocity, which is about 1/5 of the maximum. The reasons for that are a little bit complicated, but have to do with thermodynamic irreversibility of shock compression and release. The shock wave, as it turns out, conserves mass energy and momentum, but it doesn't conserve entropy. It's an irreversible compression, whereas the release does conserve entropy as well as mass energy and momentum. And the result of the non-idealness or irreversibility of the shock wave is leaving behind some fixed velocity that is actually the origin of this excavation flow field, which throws out the normal ejecta curtain. But because the maximum velocity here is such a small fraction of the maximum particle velocity in the shock, the excavation flow field is relatively slow compared to the surface rocks, which are thrown off at velocities comparable to the particle velocity itself. It's maybe a subtle distinction to make, and one that hasn't been made much before in the impact cratering business, but it really is there, and it's important in this context. Okay, so as far as the projectile is concerned and the nearby rocks, however, what happens to them is they are raised to a high pressure irreversibly and then released. In the process of doing that, heat is deposited as well as this residual velocity. And if we look at what happens on a thermodynamic diagram, this is pressure versus temperature in, pressure in logarithmic units. This equation of state, by the way, is a theoretically computed equation of state using an equation of state package called Anios, developed at Sandia. When the shock compression occurs, the material doesn't follow a thermodynamic path. It simply jumps to a point on the Hugoniot curve, given by a pressure depending upon the impact velocity. And then after it's shock compressed to some point, then it releases down an adiabat, which we can follow here, toward lower temperatures. What we see occurring as a function of shock pressure, for the lower shock pressures we release and simply come down to the state, in the solid state, at a higher temperature than we started. That extra temperature that's added to the solid is the measure of the irreversibility. At higher shock pressures, we come down in the liquid field, and at still higher shock pressures, we come down in the liquid field, eventually join the liquid vapor curve, and then follow that down, and so that we have a mixture of liquid and vapor in this field. At still higher pressures, which I haven't shown on here, we would come down on the high temperature side of the critical point and stay in the vapor field until the liquid vapor curve was intersected from the other side. Okay, so that's how vaporization occurs, and the effect of that vaporization can be seen here. This is a a sketch which is actually derived from a numerical calculation that Tom Ahrens did a number of years ago of what happens in an impact. Shortly after the impact occurs, the projectile is unloaded. That's why the outside surface is dashed. It's vaporizing. The vapor is expanding out of the crater. At the same time, the shock wave is expanding out. You see quite a bit of structure in this slide. That is there in a numerical calculation. It's mainly because release takes place at the edge of the projectile first before its body, and so there are some actually inward velocities. The structure is quite complicated, but it doesn't take very long before all that structure gets sorted out, and as the shock wave expands, it takes up a nearly hemispherical form. Ahrens didn't carry the calculations out far enough to see that. However, some Soviet calculations actually do that. You can see the hemispherical form being achieved by the time the cloud has expanded several times its own diameter. So we have the shock wave expanding out and driving atmospheric gases before it. Now, in these early stages I show here, the pressure in the gas cloud may exceed several megabars. Atmospheric pressures around are perhaps a bar at most, and the effect on the effect of the atmosphere is entirely negligible until expansion has increased the size of the gas cloud to the point where its pressure is comparable to that of the surrounding atmosphere. Remember also, as it expands, condensation is occurring. There may be a lot of gas in the initial cloud. As it condenses, it turns into a mist of liquid droplets and still lower pressures into a solid glass, or maybe condensates from the vapor. For our purposes, it really doesn't matter, because this mist of fine debris traveling out at high speed is nevertheless capable of driving atmospheric gases in front of its permeability is effectively very low. I should mention here that the velocities calculated for the edge of this gas cloud are very large. For an impact at a velocity of 20 kilometers per second on the Earth with a silicate projectile, simple calculations show that the edge of this gas cloud expands out at speeds exceeding 40 kilometers per second. So the gas cloud, edge of the gas cloud at least, moves at exceedingly high velocities. And in fact outruns the spalled ejecta, outruns the much slower solid ejecta, outruns virtually everything else. I might say, as an aside here, one reason for thinking this actually happens is that many of the craters on Venus appear to have ejecta blankets that look just like lunar crater ejecta blankets. That would be hard to understand if the atmosphere got in the way of this ejecta traveling outward. However, if the path has been cleared by an expanding vapor cloud that simply pushes the atmosphere aside and creates a vacuum for a short time, there wouldn't be any trouble in understanding those ejecta blankets. So we have at least some inferential evidence that this really does happen in the case of impacts on a planet with quite a large atmosphere. Now, I should also caution you that this high velocity is larger than the mean velocity of expansion. This large expansion velocity comes from calculations in which the expanding vapor cloud is treated as a perfect gas. This is a calculation due to Zeldovich. As I pointed out to you on the thermodynamic diagram a moment ago, at pressures comparable to what we think might occur in normal impacts, actually the silicate vapor or silicate material approaches the vapor-liquid curve from the liquid side, not from the vapor side. And we're not sure how far these Zeldovich estimates actually work in that case. This is a subject for future research that we're doing right now. We were a little surprised to find that result. If the projectile that struck were a comet, however, something icy, there'd be no problem. It's easy to miss the critical point, get to higher temperature than the critical point, and in that case, we'd have expansion of a cloud as a perfect gas until it condenses.
How does this expanding cloud create a vacuum through which these particles are then?
Okay, the question is, how does the expanding cloud create a vacuum? It doesn't really create a vacuum exactly, but by the time next slide coming up, by the time it equilibrates to the same pressure as the atmosphere, the cloud gases are much hotter than the surrounding gases, so the density is lower. It's not exactly a vacuum, but compared to the Venus atmosphere, it's good enough. Okay, let's take a look at that, in fact. There are two cases as to what can happen. For a small impact, just as for explosions, we have the gas cloud expands, and in the case of a small impact, by the time it expands to the point that its pressure equals the surrounding material, for a small enough impact, the size of that hemisphere of gas is less than one scale height, so you can treat the atmosphere as a homogeneous medium. In that case, the cloud simply expands out to the stagnation point. It's less dense than the surrounding air, and so just like a hot air balloon, it simply rises up. It forms the classic mushroom cloud. We get a nice vortex formed in here, raises some dust and rises to the stratosphere and just stabilizes there in a way that's very well known to anyone who studies explosions or volcanic eruptions for that matter. However, when the impact is large enough, if it's large enough so that when you expand the gas hemisphere to the point that it would equilibrate the pressure with the outside atmosphere, if its diameter at that stage, when it would be equilibrated, is larger than the scale height, then we have a qualitatively different expansion phenomenon. Instead of stabilizing, it can't do that because by the time it's stabilized, it's larger than the scale height of the atmosphere. In that case, the numerical calculations show that it simply blows the gases above it away and expands out of the atmosphere. It just completely blows out of the top of the atmosphere, if you want to think of it that way, and distributes its debris much more widely. This phenomenon is well known to people who work on nuclear explosions, and it's actually kind of a worry to them because in this case, with a rising fireball, most of the radioactivity stays within the fireball, and it's at least relatively localized in this fireball and in the downstream direction. If this were to happen in a nuclear explosion, all the radioactive debris would simply be spread over some hundreds or thousands of kilometers in the vicinity of the explosion. The best estimates, however, put this changeover at something on the order of 200 megatons, and nobody's gotten close to that, so it's perhaps not a worry from that point of view. However, 200 megatons is an energy comparable only to a relatively small meteorite impact, and we think, in fact, that this kind of blowout occurs starting at a crater diameter of about 6 kilometers diameter on Earth. On Mars, it would occur for a somewhat smaller crater. And it's this diameter and this process, again parenthetically, that probably marks the onset of tektites ejected from an impact crater. They only get strewn to very great distances if they can travel ballistically above the atmosphere, and this kind of blowout has to occur before that happens.
What sort of velocity does that diameter?
There's no velocity. As long as there's enough vaporization occurring, then you get this phenomenon. Another way of estimating, the way typically that's done for estimation is the amount of energy deposited in the atmospheric gas, which is typically 200 megatons, according to the nuclear explosion people's best estimates. I mean, that's in the atmosphere. Of course, an impact can deposit a lot more in the ground that won't get into the atmosphere, and so you have to factor that in when you're estimating the minimum crater size in which that will occur. Okay, so we can see how an impact might occur, might produce a large volume of vapor which could drive atmospheric gases in front of it. However, there are a couple of criteria for this kind of process, and if we can have the next view graph, I'll show you what those are. First of all, the projectile has to be fast enough to create vapor. It has to be still faster, though, than just to create vapor. It has to be fast enough to create vapor which will expand at a mean velocity equal to escape velocity. Okay? And that's what this limit is. It turns out the velocity has to be greater than a factor times well, escape velocity squared over 2, that's basically the energy or enthalpy in the vapor. And also I've included the heat of vaporization. So I said that the impact velocity has to be fast enough to supply the heat of vaporization of the material, of the projectile or target, plus it has to give it enough energy that when it expands, its mean expansion velocity is greater than escape velocity of the planet. That's what this criterion is all about. And I won't go into detail as to where the numbers come from. You can read about that in the paper. So that's the first criterion in order to remove the atmosphere. The second one is that the projectile has to be big enough. If the amount of gas that's produced, even if it's moving at greater than escape velocity, is less than the amount of mass in the atmosphere, then it's clearly going to simply transfer some of its energy to the atmosphere, and nothing or very little will be ejected from the planet. So there are these two criteria. It has to be fast enough, and when using the term big enough in the first cut that I'll have at this, we'll say it has to be greater than the mass above the tangent plane. We'll see that that's actually a little bit optimistic in a few moments, but it certainly has to be on the order of the mass above the tangent plane to the target. If it doesn't have at least that mass, it's not going to eject it. Okay, if I could have the next slide. Since it's getting late, I'll only show one of these in some detail. This is the threshold velocity for an icy projectile as a function of planetary escape velocity. And there are two curves on here. Let's look at the case for Mars. The projectile velocity needs to be just a little bit over 5 kilometers a second, about 6.5 kilometers a second, in order to at least vaporize the projectile and have a small quantity, the very fastest part of the gas, exceed escape velocity. But that's not very much mass, and that's why I call this incipient ejection. This other curve is the velocity that the projectile must have in order to eject, or in order for its expansion velocity to exceed, the average expansion velocity to exceed the planetary escape velocity. And you can see on Mars that's up around 12 or 13 kilometers a second. This is for an icy projectile with a small enthalpy of vaporization. So you can get an estimate that the mean impact velocity on Mars has to be on the order of 12 or 13 kilometers a second before atmospheric erosion will be an important aspect. The next slide, which I won't spend as much time on, is for silicate projectile. Basically, we're seeing the effect of the larger enthalpy of vaporization here, and you can see that all of the velocities are larger. You need to strike Mars, in this case, at about 14 or 15 kilometers a second. For Mars, it doesn't make an awful lot of difference in this case. It would make a little more difference at the lower velocities. Okay, and if we use the criterion that the mass has to exceed the mass above the tangent plane, we can then get a simple expression for how much mass is lost for a given cratering flux. And if we could have the next view graph, I'll show you a couple of equations. Okay, this is the mass of the atmosphere lost per unit time. This is equal to, I'm afraid I'm losing my battery or losing power here. This is the cumulative number of impacts that have occurred with a projectile mass greater than the critical mass. Okay, that is greater than the mass above the tangent plane. This is times the area, and oops, I left out a factor. There should be a factor here of the mass above the tangent plane. That is, each impact that is effective at removing the atmosphere removes basically the mass above the tangent plane. So we simply add up all the impacts that have occurred on the planet that are effective in that way, and we get the total atmospheric loss. It's fairly easy to solve this. We know the cumulative number of projectiles is some constant times the mass to a power in general. One interesting aspect of this process is, however, that because the number of projectiles increases with the decreasing mass, if you start out with a planet with some atmospheric mass, there's a critical size projectile equal roughly the mass above the tangent plane, which can remove the atmosphere. You have some of those projectiles hit the surface, the atmospheric pressure decreases, and then you find that smaller projectiles are capable of removing the atmosphere. And as the process of atmospheric erosion goes on, as the pressure goes down, smaller and smaller projectiles become capable of removing the atmosphere. And of course, there are more and more of those small projectiles, so the process runs away with itself. Most processes that you can think of that will decrease the atmospheric pressure work exponentially. As the atmospheric pressure goes down, they become less and less effective, or can at most remove only a fixed portion of the mass that's left, and so they never really get to zero. This process is capable of running the atmospheric pressure down literally to zero, simply because as the pressure goes down, smaller and smaller projectiles are capable of stripping the atmosphere away. You can solve this equation. The solution is shown at the bottom of the slide. It's a fairly elementary thing to do, and what you find is that the atmospheric pressure, not surprisingly, decreases with time in a known way depending upon the cratering flux. So as long as you know the crater flux, you can get the rate of decline of the pressure. Now this assumes a constant crater flux. We can do a little bit better. We can remember that, let's skip that. Well, put up the equation briefly, and I will not spend too much time on it. We can remember that in fact the cratering flux during heavy bombardment was originally large and then decreased, and factor that into our equations. That's done here, Thank you very much. That's done here. Simply putting in this, we can again get an analytic solution, and let's just turn that off and go to the slides, which shows the solution itself graphically. Okay, here's the cumulative crater density as a result of the age of the surface. This is from the lunar curve. The heavy line is simply the fit that we used to make the calculation shown in the next slide. Again, this is for the lunar flux. Starting at a present atmospheric pressure on Mars of 6 millibars, we simply work the equation backward. This is probably wrong to do it this way, because the present atmospheric pressure may be controlled by outgassing from the surface. It's suspiciously close to the triple point of water. It may be that the impact erosion actually reduced the original atmospheric pressure exactly to zero, but this gives us sort of an upper limit. Although I should emphasize this particular way of doing it may not mean anything, but at least it has the advantage of definiteness. We start out with 6 millibars. We go backwards in time. You can see between the end of heavy bombardment and now, there's been very little change in atmospheric pressure because there simply haven't been enough impacts. However, when we get back to heavy bombardment, we see that the atmospheric pressure could have been as high as 100 times the present pressure, which is about a bar. So that atmospheric erosion, at least during heavy bombardment, could have been effective at removing most of or could have effectively removed a 1 bar atmosphere to leave us with our present very low pressure atmosphere. Okay, now this simple picture is subject to some caveats, which I want to bring forth for just a couple of minutes. Okay, first of all, this is a illustration of the geometry with the atmospheric scale height, of course, vastly exaggerated, so you can see what's going on. Here's the tangent plane, and we're going to consider an impact that occurs, and this is the mass above the tangent plane here. We'll consider things with material or ejected from the vapor plume moving off at different angles from the tangent plane. One thing you can see fairly obviously is the amount of mass in an atmospheric column vertically above the impact point is quite a bit less than it is along the tangent plane. That is, the atmospheric mass is concentrated toward lower angles. If we have a hemispherically expanding gas cloud, that doesn't couple very efficiently to an atmosphere in which this extreme concentration toward the tangent plane occurs. So there's a mismatch here between the expanding hemisphere of the gas cloud and the structure of an atmosphere. Underlining that a little bit, this is this is for Mars's atmosphere, mass above the tangent plane in kilograms as a function of zenith angle, and this is the mass in 1/4 degree solid angle bins. You can see that there's quite a bit of variation. If you go to 90 degrees, the amount of mass is several orders of magnitude higher than the mass along the zenith, underlying this difficulty in coupling efficiently to the atmosphere. In order to deal with the situation, we obviously can't use a simple model of a spherically expanding cloud. What we do is something that the Soviets have discovered called the sector model. We assume that, or look at the mass in some angular interval. We use our expanding gas cloud model to start the expansion off. We assume everything is uniform in our hemisphere, and then just ask how much mass is there out in the atmosphere, and compare the amount of momentum in the expanding gas and dust cloud to the amount of mass of the atmosphere. Average the two together and ask if the momentum of the gas cloud plus the atmosphere in this sector or this angular interval is greater than escape velocity. If it is, we assume that that atmosphere is stripped away. If it's not, we leave it with the planet. If we use that sector model and the Zadovich and Razier gas cloud model, the results are this. This is impact velocity here. This is the atmospheric mass lost in units of mass above the tangent plane. So here's 1. This is our assumption. You can see that there's some dependence upon velocity. The higher velocities are more effective at removing mass, not a real strong dependence compared to other things. The main dependence is on the mass of the projectile. And although I didn't write these masses out in units of the projectile or of the mass above the tangent plane, it turns out that we have to get up around 10 times the mass above the tangent plane at velocities of 20 kilometers a second before we can get the entire mass stripped because of this coupling inefficiency. I should mention, though, however, one thing that we assumed is that the gas cloud expands radially outward. In fact, you'd expect that as the gas cloud expands, some of the low-angle expanding material ought to get pulled around towards still lower angles and cut below the tangent plane. That may pick up some extra efficiency. So this estimate of inefficiency is actually kind of conservative. However, one thing we've learned in doing this is we're going to have, in order to get a better handle on what goes on with atmospheric erosion, we're going to have to do a very good job in calculating the both the atmospheric structure as well as the effects of the impact, because all the action is at relatively low angles in places where it's hard to do calculations analytically. So we'll have to do numerical calculations, and they'll have to be good numerical calculations. We can't slough off the details. What this implies for the atmospheric pressure decline, here are some curves. This is the one that you saw before, where we assume that the effective mass in stripping the atmosphere is equal to the mass above the tangent plane. That's the curve labeled 1. This is assuming the mass is 5 times the mass above the tangent plane. Here is assuming the mass that's effective is 10 times the mass above the tangent plane. You can see in the 10 times case, we can get back to a pressure of only 10 times the present pressure, or about 1/10 of a bar at the beginning of heavy bombardment. Whether that's enough to explain the observations of water on Mars is something else that at the present time I'm not sure. I'm also not sure what this number is, whether it's 1 or 10. It's somewhere between 1 and 10, but we don't have a good idea for exactly what it is. But I thought it was important to share with you the possibility that it may be quite a bit larger than 1. Next slide, or next view graph, if I could have that. These will be the last couple view graphs. Okay, if we could turn that around 90 degrees, please. Okay, this curve, one of the things that there have been many objections to with a slide that I just showed you is that the time scale is pushed back to early in Martian history. Everything's 4 billion years. And people ask me, well, how does that relate to Mars? So people have favorite ideas of when things took place at different parts of Martian history. And depending upon their prejudices, they object to the ages on that. In fact, we don't have to be tied to ages. All we need to do for atmospheric erosion is know how many impacts have occurred of a given size since that interval of interest. And that's the way actually ages or stages are assigned to Martian surfaces, by their crater density. And so this is a plot of atmospheric pressure with respect to the present atmospheric pressure. These numbers don't mean anything but stages. This is not a scale of numbers. This is what I think is called among geochemists a Caltech plot, something against nothing. Non-Caltech geochemists. At any rate, what these numbers refer to as 1, where there are points, is at the time of the most ancient cratered highlands. That's using the crater density that's actually observed. And this is old plains. This is northern plains, the so-called end of the Amazonian, and this is the present time. And you can see if you go back to the most ancient highlands, and we know the crater density, we don't get a very different picture with a mass that's effective mass that's equal to the mass above the tangent plane. We find the atmospheric pressure could be 100 times larger than now. If it's only 10 times the mass, or if it's as large as 10 times above the mass above the tangent plane, then we get a factor of 10.
Excuse me, Jim, I understand
Yeah.
that in the sense that I would think the craters that formed very early in Martian history would have essentially been obliterated by the ones that came later in heavy bombardment. And not only that, but any valley networks that formed in the earliest times would have also been obliterated. So
Exactly. But we see valley networks. We see valley networks on plains for which we can measure the crater density, which are generally the old plains crater densities. Okay? It's true with the most ancient highlands, if they are saturated, this curve could be much higher. Okay, so this is actually for the ancient highlands, for just this particular set of values, this is a conservative estimate in that sense, because the total number of craters that have impacted since those plains began could be larger, because craters obliterate craters. In the non-saturated, though, areas in the old plains, it's probably a reasonably good representation. And we see valley networks superposed over those plains.
But don't you want to explain the pressure at the time that you see the valley networks?
Yes, and the valley networks are that you can see are generally at this time too. Okay, and further back, where we can get maybe a factor of 10 increase in the atmospheric pressure. It's not enough to satisfy Toby-Owens' constraint of 1 bar. I mean, going back from the present atmospheric pressure, unless you give it a boost from some other cause. It is fairly easy, though, to go back here. Once you get a factor of a couple times, you can get above the triple point of water and make water stable on the surface. That's not a problem. The last plot is a variation on this one, in which I've taken the pressure at the time of the northern plains to be 1 bar, and gone forward in time. You can see that the present time now, at the present time, the pressure wouldn't be much lower than 1 bar due to atmospheric erosion. The reason I choose this particular time of the northern plains is that my colleagues Vic Baker and Robert Strom at University of Arizona are presenting a scenario for Mars' surface which not only was damp at that time, but in fact had great glaciers, it had polar seas, it had water covering the surface of the planet. If you want 1 bar pressure at that time, you're not going to be able to get rid of it by atmospheric or impact erosion of the atmosphere. You need to play some other trick in order to dissipate the atmosphere from that time. So impact erosion doesn't work there. In conclusion, then, let me say that atmospheric erosion appears to be an effective agent during heavy bombardment on Mars. It's not very effective at the present cratering rate. It is sensitive to atmospheric structure near the horizon, the curvature of the planet's surface. You cannot do an impact calculation to determine atmospheric erosion by this means without putting the curvature of the planet in it, something nobody has ever done in an impact calculation. I think we need to do more numerical work before we know what this threshold is much more precisely. Within a factor of 10, though, it appears to be the mass above the tangent plane. Atmospheric or impact erosion probably does not fractionate gases, so far as we know. So if you're trying to explain a difference in the abundance of, say, neon and krypton on the surface of Mars, impact erosion will not be effective in doing that. It appears to remove atmospheric gases wholesale. On the other hand, it does have the property of separating condensable from volatile species. And what I mean is, if we, say, brought the atmosphere of Mars in by comets and CO2 were non-condensable formed in the atmosphere, it's much more liable to be removed by impact erosion than, say, water, which might condense out on the surface. So in the case of Mars, we could potentially pump up the abundance of water on the surface of Mars with respect to CO2 by impact erosion during accretion. It's a process that really hasn't been looked at, but it certainly deserves some consideration as a possibly important process. And I should mention that this kind of process also may have been important in more exotic areas like Triton and Titan for changing the proportion of condensable to volatile species. And I'll stop the main part of this talk here. Thank you.